Hello, and this week we'll be looking at two more device fabrication schemes. And the first one I will mention is doping. Doping is a process we put three or five materials into the silicon or the substrate in order to make it into a P or N types. And why do we make our silicons P or N types? Well, to create excess carriers for conducting electricity. That's why. There are two methods for doping a silicon. The first one is diffusion method. Diffusion method takes in many steps, but it's pretty simple. First, there's pre-deposition phase, where we put the dopants on top of our silicons, and next, we expose the dopants on high temperatures in order to drive in and infiltrate the substrate layers. And also, that activates the dopants and makes the material P or N type. The next method is ion implantation. Ion implantation, we make the dopants into ions, and through the high electric field, we just crash the ions onto the silicon substrates, hence bombardment method. As we learned throughout the course, we know that both methods, diffusion and ion implantation, usually have their pros and cons. But however, in doping, that doesn't really apply. Well, that's because we need to have a shallow source-drain junction. And we need to have shallow junction profile because of short channel effect. Put it briefly, short channel effect is a problem that caused because the horizontal electric field, known as source drain electric field, and the vertical electric field, the gate field, the both battle each other, and that causes the effect. So it is really important to have a shallow junction, and only ion implantation offers that kind of feature, because in diffusion doping process, even though we place the silicon on top in the pre-deposition process, however, it will diffuse, it will just keep going deep through because of the drive-in phase, the activation phase. So ion implantation is much preferred in the industry. The last thing I'll mention is advanced doping. When we dope into ion bombardments, there's some lattice damage, and since there are so many ions, the lattice damage might be devastating on the device. Hence, so the lattice structure just becomes much more worse. Hence, we'll end up with lower mobility. So we used a heated ion and some more thermal annealing, and that will restore the lattice structure of the device. Well, see you on part 2. Welcome to our part 2 of our review video. In part 2, I'll be discussing about the metallization process. Metallization process is a device fabrication process where we stack or put our metals onto our finished device. And the metals we'll be putting on will be on the gates and the source drains and other planes if it's necessary for our fabricated device. So, as we learned throughout the course, we need to have a low source drain resistance, or hence contact resistance, for our maximum efficiency on our finished device. So, in metallization, there is a process called silicide, and the silicide is a compound that mixes between silicon and the metals. And the concept of silicide is that if we put our bare metals onto our bare silicon, that creates a Schottky junction, as you guys already knew that. So in the Schottky junction, because of the Fermi level pinning, the electrons have to jump through a large gap or a high wall. However, if we put a silicide on it, the work function between the silicon and the metal, the silicide will work as a stairway or just a stepping stone for easier electron jumping or access through the metals, hence a lower resistance. Not only we could achieve a lower resistance by changing the material properties on our materials, but also the materials on the metals where we use for metallization process, and that is called a damascene process. Damascene process, we use copper because copper has a low resistance, so we can achieve some profits there. However, there's some problem. Copper usually diffuses through the silicon if we use the bare copper, so we implant the damascene process, and we'll be looking like this. And the idea of the process is we use another layer of metals to coat the silicon. So the copper we pour in for our metallization doesn't diffuse into the wafers and create some problems. Well, that's about it. Thank you for listening, and thank you for watching.